Okay, so far we've talked about the API and we've talked about the different components. We're running a little bit behind here, so this section is on the kind of the inner workings of a generic component, and I'm going to try to go through it really fast. So for someone from Alabama, it's kind of dangerous for me to try to talk fast, but I'm going to try to do it. So all our components right now are written in C++. We've kind of mentioned this before. Some of the rationale behind that, we thought it'd be a natural transition point for our Asterisk community developers who might wish to start looking at Asterisk SCF. And of course, high performance associated with C++ applications. We have done some alternative implementations in other languages, particularly of the routing service. They're a little bit out of date now, but we've implemented it in Java and C# and Python. So they're probably not up to date with the current system, but if you had some curiosity about what the code would look like in other languages, they're there for you to look at. And also some of the configurators for each of the components are written in Python, and our example hooks are in Python. Okay, so Josh touched on the component-based class. It's basically something that's there to help with coordinating startup and shutdown of components and other common things that are kind of boilerplate so that we can have some consistency in all the different components. I'm going to breeze right through this. So the base component class has several different categories of operations on it. It implements all the interfaces required to be an iSpot service, so you don't have to worry about that at all. The initialization process uses the template method pattern. So the template method pattern, if you're not familiar with it, it's basically a set of sequences in an algorithm without any detailed implementation. But for every step in that algorithm, in the initialization process, we provide a default implementation that works for most every case. There are certain steps in the process that you just have to override and provide your own implementation, and the compiler will gladly tell you which ones those are. Okay, so there's default implementations, pure virtual operations have to be overridden. Okay, some of the helpers we have, these first two operations here, the managed primary services, managed backplane services, those are a way of registering services with one of the two adapters. If you recall, you probably heard a little bit in the ICE overview about the object adapters. We provide two adapters in Asterisk SCF for each component. The primary service adapter is where the functionality specific to that component, it's kind of domain functionality. For example, the SIP session gateway's SIP interfaces or the routing services routing interfaces. Those are published on the primary service adapter, or registered with the primary service adapter. The backplane service adapter is for things that are more plumbing oriented to being an Asterisk SCF component. Things like replication, things like the component service interface to manage its life cycle and things like that. The locator, the wrap service for registration process, kind of like the smart proxy Josh mentioned earlier, which kind of alleviates some of the problems with race conditions on whether or not the service locator there. The smart proxy was to handle the case where I'm trying to access some service that's remote from me, but I can't really get to it yet. Well, this is kind of the complementary for that for services that I'm publishing. I've got some service, I want to put the proxy to my service into the service locator. Well, this will do the retries and so forth until the service locator is available. Replication within a component, as it has already been stated, we have for any component that needs state replication in order to support failover, we have a complementary state replicator specific to that component. State changes flow from the active component and will go to any registered listener. This is really oversimplifying things a bit, but that's essentially what happens. Thread pools and work queues. This is some functionality that we've created to help in dealing with concurrency. It's a very common problem when dealing with multi-threaded applications. Let's see if we can. Okay, so the thread pool is basically managing a collection of threads. Each pool owns a work queue. I'm going to go right to the graphic here. Okay, so basically a thread pool implements a work queue. You can push in queue objects to be processed on a thread into that work queue. The thing that you push into it for a specific object to make that object thread safe can itself be a work queue. So what you see here are across the bottom where that vertical stack is, that's a work queue that's queued up into the thread pool to be processed on a specific thread. Let's see. So access to the state for that object is limited to a single thread out of the thread pool. This keeps it doesn't do away with locking, but it centralizes locking into the process of enqueuing work into the work queue and taking the work out. So all in the rest of your code, if you follow this paradigm, you don't have to worry about locking state for corrupting state and things like that. So it does take a little bit of a paradigm shift. What you're basically doing is taking an operation and encapsulating a single operation into a single object that we refer to as a work item. So here's an example of a simple work item. It implements our work queue's work interface and has an execute method. And when it's ready to execute at the appropriate time, it will get executed and do its stuff in a thread-safe manner. Right now, our SIP session gateway makes extensive use of the thread pool and work queues. The bridge manager does as well. And now here's the point we were really trying to race to get to in our last 15 minutes. Example call scenario. So the components, were there any questions on the stuff I just flew through at blazing speed? Okay, excellent. Yes. So the major components involved in call processing. SIP session gateway, of course, it's talking to the SIP endpoints. The media RTP PGA media component is setting up and passing media. The routing service is involved to locate the endpoints. The bridge service is bridging the two endpoints together. And service discovery is used by everybody to find all the different services in the system. And media format generic and ICUtils involved. Okay, so we're going to have, as you might have guessed, we're going to have Bob call Alice. They're both going to use G711. And for the first instance of this, we're not going to use any authentication. So we're just going to go right to the UML here. So Bob is some endpoint outside of Asterisk SCF, but he is registered with the SIP session gateway. He sends an invite, SIP session gateway over SIP. The SIP session gateway interprets that and turns that into Asterisk SCF operations. The first thing that happens is he tries to do a locate on Alice in this case, and then we create the media session. Right now, and the point of this being done so early is to make sure that we can establish a connection between the two. Okay, invite, let's see. So now he tries to route the session. The router will do lookups, and he actually ends up calling back to the SIP session gateway. It could be a different SIP session gateway, or it could be some other technology gateway that's implemented in the future. But then the point is he finds the endpoint that's being routed to. The routing service is then responsible for creating a session. And let's see, that's the media session in this case. And then It's not there yet. So now the routing service is going to create the bridge. The bridge will add itself as listener to the two endpoints, and then it returns a completed notice back to the routing service. The bridge service then gets the streams associated with those two endpoints, and then goes through the process of setting up, connecting up the sources and sinks for the media streams. Okay, and now the routing service will send the invite. So how does it decide which codec should be in the SDP? Josh, you want? All right. So the ringing is passed back. The bridge service is, as we saw earlier, registered as a listener to the endpoints. So it's listening to indications that happen, which in this case is ringing. It flows all the way back to Bob's SIP session gateway, which could be the same gateway SIP session gateway that Alice is connected to. It turns that into the SIP ringing 180 message out. Then the OK comes. The SIP session gateway responds with acknowledge and again forwards an indication on to Bob. Does that make sense to everybody? So, Bob invites Alice to dinner and a movie using their native language, presumably. Hopefully those are compatible. Bob's reputation precedes him, and Alice promptly hangs up. So the SIP buy comes in. Again, the indicated is passed on to the bridge service because he is a listener of that endpoint. The indicated is forwarded onto Bob's endpoint, which turns that into the SIP message buy. And then it processes the OK and tears down the endpoints or the sessions for those endpoints. It's not shown on here, but it happens. There's actually quite a few messages that are being passed around here. For example, I think I only showed the service locator here in the very first instant. It's actually involved a lot more than that. But what happens is the components end up caching up. Once they know where one other component is, they'll cache up that interface and keep it around. So it may not have to go try to get it again. Now we're going to talk about extension points. Now we talked about extension points and hooks. And for every extension point, which is basically a point in the process of a component where the developer of that component has decided some custom logic could be inserted here. And the way that logic is inserted is you encapsulate that logic into an object called a hook, which has a defined interface in Slice. And then the component has an extension point interface for you to add hooks to it. So you register the hooks, and off you go. Let's see. So here's a case with an authentication hook added to the picture. The invite comes in. The SIP session gateway checks to see if any hooks have been added for authentication. It finds one. It sends the challenge request to the hook. It gets back the credential information that's going to be required. And there you go. Yeah. Okay. So yeah, I kind of oversimplified this. What actually happens is the authentication hook goes to the service locator, finds the SIP session gateway, and adds himself. Is that right? Yeah. Yeah.
That's an area where we expect latency if doing a dynamic lookup to be a problem. So we don't. If you want to put things to an extension point, you have to break dynamically set yourself there. Say, I want to be called at this time. So that we don't add the cost of going and doing a lookup every single time that goes. All of them. They're all going to be like that.
Yes. If you notice, and again, that's an area where I'm not showing quite every interaction because this would just become so busy. But the routing service, for example, let's see. If you notice right here that second set of interactions there, the routing service added itself as a listener for indications on that endpoint. So if Bob happened to hang up before the call was ever even connected or before the phone ever even rang, the routing service is smart enough to shut the session down. Yeah. Sorry. So any other questions on call flow?